All right, so we're going to look through some of these review questions for your quiz on exponential functions. All right, so this first question right here about modeling, this is the only one that is not in that Kahoot. All right, so it gives you a function, y equals this whole mess to the x power. It says that it models the U.S. population from the years 1900 to 2000. And x is the number of years since the year 1900. Okay. According to the model, what was the population in 1980? Okay, so this means that x is equal to 80 because x was the number of years since 1900. All right, so all I'm going to do is I'm going to take 80 and plug it in for x right here. All right, so y equals 81.1 times 1.0126 to the 80th power. All right, and this is going to tell me the U.S. population in the year 1980. Okay, so it'll be 81.8. Let's see here, 1.0126 to the 80th power. There we go. So in 1980, the population was 222 million. All right, because the answer was in millions. Awesome. All right, the next question is about the interest formula. This should be your first one on that Kahoot if you're playing that. Use the compound interest formula right here to figure out what $7,500 will grow to in 9 years at 5% interest, compounded semi-annually. Okay. Geez, mouthful. All right, P1 plus R over N to the NT. All right, so the 7,500, that's my initial investment. That's the principal. So I'll plug in 7,500 there. 1 plus the interest rate, R, that's going to be 0.05. You have to put that in as a decimal. N, all right, N is the number of times that it's compounded annually. And since this one is compounded semi-annually, that's going to be a 2. All right. If it was monthly, it would be a 12. If it was quarterly, that would be a 4. And then raised to the NT power, that's going to be 2 times 9. There we go. And then we'll enter this in, and that should tell us what that money is going to grow up to be. Okay, so we'll have 7,500, 1 plus, and then you can either just divide these numbers or make it into a fraction using alpha y equals. I'll just divide them. 0.05 divided by 2. All right, and then we're going to raise it all. So use that little caret key to the 2 times 9 power. There we go. 11,697 and 44 cents. All right, moving on. All right, the domain. So domain are the numbers that you are allowed to plug in for x. And it's also like how far left and right the graph goes. So you do need to be familiar with what the graph of this looks like and just what the general domain of these are, of exponentials. All right, the graph for the kind like this, the ones that display exponential growth, all right, they're going to be like a straight line here. This is our horizontal asymptote. And then it's going to spike right here. It's going to start growing exponentially as x gets bigger and bigger. All right, it's going to go to the left forever, and it's going to hug this x-axis, and it's going to go up and to the right forever. So it goes left forever and right forever, all real numbers. There's no limit, there's no restrictions on the numbers that we can plug in for x here. All right, we're allowed to plug in any number for x. All I guess if you had to, you could graph that on the calculator, y equals 3 to the x. Just the graph doesn't really do it justice according to that picture. It's hard to see what's going on there. All right, the next question. What is the range of 4 to the x minus 5? So they're asking what's the lowest it goes and what's the highest it goes. Again, you're going to need to be familiar with what the graph of these look like. Okay, y equals 4 to the x. It's going to be the exact same looking graph as this one. But because of the x minus 5, this is just going to shift it to the right 5 units. All right, so it's still going to go left forever, but since it's getting shifted to the right 5 units, it's going to go to the right a little bit more before it starts spiking up like that. Okay, but the range for all these exponential functions, since they kind of hug this x-axis right here, they never actually cross the x-axis. The lowest it gets to is 0. It actually doesn't get to 0. It gets infinitely close to 0 right here with that asymptote. So the lowest it goes is 0, and the highest it goes is infinity. All right, so 0 to infinity, but I'm going to put parentheses on the 0 because it doesn't actually get to 0. All right, horizontal asymptote. All right, so y equals 1/3 to the x. You could graph it if you want to, but again, it's not going to give you very much of a picture. All right, so this one, instead of it swooping up like that for exponential growth, this one's going to be the reverse of it. All right, it's going to start super high, something like this, and as it goes to the right forever, it's going to get closer and closer to this x-axis. All right, closer and closer to 0. So this type is going to model exponential decay, but what they want to know is what this horizontal asymptote is, and it's just y equals 0. All right, that's the value that it never quite gets to. It's what the value of the function is as x gets really big. So if you do 1/3 to say like the 1,000th power, you're going to see that this is getting closer and closer to 0. Okay, question 5. Vertical asymptote of 3 to the x. These do not have vertical asymptotes, all right? And the reason is because there's never any division by 0. All right, so exponential functions do not have vertical asymptotes. All right, something that decays exponentially. So I mentioned that this one represents exponential decay. The graph kind of goes, as it goes to the right forever, it's kind of leveling off at 0. And these types represent exponential growth. And all this has to do with is the base, okay? If this base, if it is between 0 and 1, all right, if it's on this interval, it's going to represent exponential decay. All right, so if we had 1/3 there, that would be something that decays exponentially. But if it's bigger than 1, that's going to represent growth. All right, that was why 3 to the x grew exponentially. So we want one where the base right here is between 0 and 1. All right, 5/3 is bigger than 1, so it's going to grow. 5 is bigger than 1, so it's going to grow. This one is between 0 and 1, so it's going to be exponential decay. All right, the y-intercept. So the y-intercept is right here, and if you want to graph it, I guess you could, but all you do for the y-intercept is you plug in 0 for x. So what you got here is y equals 5 to the 0, and 5 to the 0 is equal to 1. So when you plug in 0 for x, you get 1 back for the y value. All right. Y equals, again, they're asking for that y-intercept. So it's 2/3 to the 0 is what we're doing. We're plugging in 0 for x. All right, 2/3 to the 0, that's equal to 1. And then you're just adding 2 to it. So the answer is going to be 3. Basically, the original graph of y equals 2/3 to the x had a y-intercept of 1. And since we're shifting it 2 units up, the y-intercept just increases to 3. X-intercept, these do not have x-intercepts. Right. Yeah, I showed you the graph earlier of this one. As I said, it never actually crosses this x-axis right here. All right, it just gets closer and closer to it. And that's because if you plug in 0 for y, your normal procedure for finding an x-intercept, this equation has no solution. You cannot plug in a value for x so that you get 0 back as an answer. So, if we shifted this thing down some, if we shifted it down 1 unit, then it would have an x-intercept. But the way it is right now, it doesn't have an x-intercept. Cool. All right, we got an exponential equation now, and this is the type where you have like bases. All right, so the goal is to rewrite each side of the equation so that they have the same base. All right, so we need a common base for the numbers 4 and 1/16. So I could convert them both to like 2 to some power. 2 to the 4th is equal to 16. 2 to the 2nd is equal to 4. But I can express this one as a power of 4. So I've got 4 to the 2x plus 5. 4 to the 2nd is equal to 16. 4 to the negative 2nd is equal to 1 over 16. All right, the negative just turns it into a fraction. And now, since the bases are the same, we can set these two exponents equal to each other and solve. Subtract 5 from both sides, you'll get 2x equals negative 7, and then divide by 2. X equals negative 7 over 2, or negative 3.5. Of course, you could just plug in these answer options for x, and then just see which one gives you 1/16 if you had to. Right, one more of those exponential equations. 25 to the x and 125 to the x minus 3. Okay, so I'm not able to take the 125 and write it as a power of 25, but I can express both of these as a power of 5. So 5 to the 2nd is equal to 25, and I've got all of that raised to the x power. And 5 to the 3rd is equal to 125, and I've got all of that to the x minus 3. So the rule I want to use here is I've got a power to a power, so I'll multiply the exponents. 5 to the 2x, and then I'll multiply the 3 times this x minus 3. I got to distribute though, so it'll be 3x minus 9. And now I can solve this equation. Since the bases are the same, the exponents must be equal to each other. All right, I'm going to move my 2x over here, so subtract 2x. And I'm going to move my 9 over to the left side, so add 9. Okay, cancel, cancel. I'm going to have x on the right and positive 9 on the left. And that's my answer. All right, I think that's it for this one. The next bit is going to be on, geometric sequences.